So we're through vector analysis, vector algebra, and reminded ourselves that there are fundamental geometric definitions of all of these things that you've been kind of using comfortably for a while, probably. And now vector calculus. I suspect a lot of this is review, but it's good to have that review before we really plunge into things like potential theory. So we'll talk about the gradient, the geometric thing that we really would like to know. And this might be new, is we'll define a del operator. In fact, it's a vector because it transforms like a vector. And then in a later video, we'll talk about div and curl, and then get crazy with it and higher order derivatives. And there's a lot of freedom and wide space where you can play in and make whatever sort of wacky derivatives you want within reason. So I'm constrained to a 2D chalkboard, so this is about as good as I can get. And let's consider a scalar function. Which in general in physics might be something like a function that takes a coordinate x, y, and z and then maps it to a single number. Some number, we'll call it a. Might be a real number, might be a complex number. It's not a vector, we're not there yet. We're starting with just plain old ordinary scalar functions. And we're going to introduce a little bit of notation so we can talk about this in a little more kind of formal mathy way. Is that this takes 1, 2, 3 real numbers, and then until we get to quantum mechanics or later in this course when we do complex analysis, spits out a real number. So 3 real numbers in, 1 real number out. We actually are going to denote f as a mapping from 3 copies of the real line, so r superscript 3 copies of the real line, and it maps to just 1 copy of the real line. So 3 real numbers in, 1 real number out. If this function, for instance, depends on time, it would be r3 plus 1. So you got the time dimension too. Sometimes that gets denoted in a specific way, but we're not there yet. So just be aware that we'll start talking about scalar and vector functions with this type of notation, just so we know what sort of creature it is. OK, so let's pare this down to just 2D, because that's what I can draw on this board. So in fact, this f is a function that maps a point on the xy plane to some height, some real number. So this would actually be f of xy equals some number, z or a or something like that. So this would be a mapping from R2 to R. OK, and questions that I might want to ask is how could I increase or decrease this function as much as possible? And you guys probably know that that is a mathematical operation known as the gradient. So del f will tell you the direction of greatest change of this function. So that's the geometric idea of we'll call it direction of greatest change. OK, so in terms of this notation, what do we actually call del f? Del f is a function in and of itself, and we would say that del f is a mapping from what to what. Take 1 second to figure that out. What do I put into it, and what do I get out in this particular case where I'm drawing it in 2D? So I have to put into it a coordinate. In this case, my coordinate system, because I'm on this 2D chalk whiteboard, is r2, xy. But what do I get out? So I actually get out a vector. So you have to tell me a direction in the xy plane for the direction of max ascent. So this is a mapping from R2 to R2 in our new terminology. So that's probably a bit of a review. I'll write out the coordinate description of del f in Cartesian coordinates in 3D. And then we'll talk about this, which is a new thing. So in 3D, del f has a coordinate representation. And dang if this isn't laborious. Again, f in Cartesian coordinates is a function of x, y, and z. So del f would be given by partial f partial x I hat plus partial f partial y j hat plus partial f partial z k hat. Kind of gross. And later on in this course, we'll do this in non-Cartesian coordinates, like cylindrical or polar coordinates, which is going to be really fun. So gross. We're going to define a vector, and it turns out to be, by our new definition of vector, a real honest-to-goodness vector called del, or the gradient operator, which is just the derivative part. So we're going to define gradient operator. Or casually, we just call it del. And I'm going to put an arrow hat over this, indicating that truly it is a vector. And as a bit of a side note, this is why it's a vector, is it transforms like a vector. So remember, that's our new definition of what a vector is. So it transforms properly. Again, we haven't done reflections, but that's pretty easy, so I'll just do this with rotations. So pretend that this is a rotation matrix. And if I look at one component, which I'll just call del f, del x. K is good enough, so it's one random thingy. And I want to transform that. What I have to do is think about transforming the coordinate. So you'll get in trouble with this in the math department, but in a physics class, this is totally okay. You think about del xj as a little piece of xj. So this might be the x, y, or z coordinate in Cartesian coordinates. Clearly, this is this thing, right? So we're just taking the total derivative, partial derivatives, and you can see that these cancel clearly and gives you this. But aha, what is this? This is the rotation matrix. So what that is a jk. Right. So rotation matrix, this is the correct transformation matrix that turns a vector into a vector. So del actually does transform like a vector. So you can see that the del piece, if you remove f, this is del transforming correctly. Okay. So that's just why it's called a vector, because again, it satisfies our new and improved definition of vectors, which is things that transform according to certain properties. More important is how you actually use this, and this is probably going to be a bit of a review. If there's a reason to give you this problem, it's because we have to put some physics caveats on things that you probably didn't get in your multivariable calculus class, is that things have units. So let's do this in 3D Cartesian coordinates. And let's say that we have a function that looks like this. And the reason I have to put this z0 there, it's a constant, it's just got to have units because the argument of a natural log has to be unitless. Arguments of sines, cosines, tangents need to be radians for us, and natural logs and exponents need to be unitless. So from here on out, we're going to forget things have units, but I'm going to point out that these must be unitful. So Okay, so these are constants, and just remember they're unitful. That's what distinguishes math class from a physics class. So what we have is a function f, and this function f is a mapping from R3, this is just a number to R, and what we want to do is calculate del f, just as a bit of practice, and I'll put the arrow over this because we now know the gradient operator del is vector. And this is a mapping from, R3 to R3. So vectors go, vectors go in, vectors go out, triplet of real numbers in, triplet of real numbers out. Okay. And nice Cartesian coordinates should be pretty straightforward. I have r hat, partial f, partial x, j hat, partial f, partial y, k hat, partial f, partial z. So that's I hat partial m partial x is 2 alpha x y j hat, I have alpha x squared, and then k hat, and we'll just ignore that. Well, let's not ignore the z hat because I labored to put it in. Beta z naught over z. Okay. Great. So I hat, j hat, k hat truly is a vector. We got out the right species of thing that we're supposed to put in. So we'll do a couple more examples of that in the in-class section. So again, part of what we're doing in this revisiting of some basic vector stuff and now less basic vector calculus is we want to get some geometric insight into what these things are and what they mean. And you can make really powerful arguments in physics kind of based on just the idea that certain things should be invariant of coordinates. So let's just define an increment of length. And before we do that, we have to define an increment of displacement. So I just want to move a little bit on my coordinate system, my x, y, z plane, if you're thinking about Cartesian coordinates. And the way that I would denote that is I dx, j dy, k dz, right? So this is a 3D vector, but it's a differential vector. It points in some direction. And this can define our total differential. And again, we're thinking about f of x, y, and z, a scalar function of 3 coordinates. So total differential, which is basically how much f itself moves. In 1D, this is a well-defined question without any additional information. So you do a little bit of dx, df changes, right? But now it's ambiguous because, well, how did you move? Did you move in the x direction, y direction, z direction? So our total differential, we need to specify some direction. And the gradient is one of the things that helps answer that question. So I move in some direction, and the gradient of f tells me what my total change in df is. So, and we can also use this to answer some questions that you were first exposed to in pre-multivariable calculus, freshman level electricity and magnetism. So the idea of surfaces of constant potential, which was probably just very hand-wavy, can actually be expressed really easily in terms of gradients and differentials. So let's say, for example, I move in a direction that's perpendicular to this. and I just write down this equation. So I have a function, I take its gradient, I have this gradient, and what I do is I just define what del f.dr, define del f.dr equals 0. So I could do that, for example, with this, and I'll do that in a second. But first, like, why would I do such a thing? So write down the equation, and I solve it, so I find out, the curves, for instance, for which this is true. What are those curves? So this is what an equipotential is. So this is basically a hypersurface of zero change. So I'll try to draw this again. So I've got some wiggly surface, and here are at least two dimensions of it, x and y, and there's f. And here's the direction of greatest change, del f. So what happens if I have zero scalar product? Don't worry about the differential nature of these. I'm just talking about a dot b equals 0. Well, that means that a and b are perpendicular. So I'm moving perpendicular to the direction of greatest change. It's just like a little differential motion. Basically, I don't want to go up or down the mountain, right? So this is like a line of constant f. So what this equation defines is a hypersurface of constant f, whatever that scalar function happens to be. Scalar function could be the electric potential or something like that. Scalar function could be just normal potential. Scalar function could be height of a mountain, for instance. Okay, so how would that show up with our example? Del f dot dr equals 0. Well, I have the x part, so that would be 2 alpha x y dx plus alpha x squared dy plus beta z naught over z dz equals 0. And what you see is we have a kind of spooky looking differential looking equation. And what we'll do once we get into integral vector calculus is talk about how you'd actually get solutions of this.